I had number 24, which included both f of x and g of x. And the first thing I did was I found the domain for both of them, and since f of x had an odd degree and g of x had an even degree, found the domain for both of them to be negative infinity to positive infinity. And then once they were together in an equation, I put f of g, which became f of 2x squared, and then in the f of x equation it became 3 times 2x squared plus 2, which then becomes 6x squared plus 2, and since it has a 2, it's an even degree, which makes the domain negative infinity to positive infinity, which is all real numbers.
Questions on 24? So I believe 14 and 18 were good problems involving fractions. I'll pass around a stapler too. I think I'm just going to collect this just to take a peek at it. So if you need a stapler, it'll be coming around. So we'll start at number 14. And you'll see that like fractional equations are going to be something that we'll continue to work with and build on. We've been working with fraction powers, but all of chapter 8 are equations involving fractions, so something that like as the year progresses we'll just kind of continue working with fractions so that by the end of the year you're really good at working with fractions without a calculator. I'm doing trig right now in my honors trig and pre-calc class, and it's all fractions, so they're really good at fractions because we've done fractions so much. So like trig, every number we work with in trig is a fraction. So you'll get like by the end of the year you'll feel very confident with fractions, so that next year going into trig and pre-calc you should be able to kind of pool that material with you. All right, so for 14 has g of h of x, and the three functions that we're working with, two of them here, we have the g is a fraction and the h is a fraction. The f function is not a fraction, it just has 2x plus 3. So yesterday we talked about composite functions. And last Friday we talked about combining functions. So a composite function is an operation that you're doing on two functions, but it's like using a substitution operation. So taking one function and substituting it into another. So right here we have g of h of x for number 14. So the first step would be to take out this h of x and replace it with the equation that represents h of x. So you still have g on the outside, but h of x is now x plus 5 over 2. So what do you do next? So we have the h function. We took out h of x, replaced it with its equation. So what would be the next thing that you would try and do with this problem? Melanie?
Now you do the g function, but you plug in the h function for x.
Right, so this here is going to replace x in the g function. So the g function has a 3 on the top, and then it says x plus 1. So in that x space, we're going to put x plus 5 over 2, because that's replacing x. So you're taking x out, God bless you. You're replacing it with whatever's in parentheses. So I'm just going to rewrite it so I don't have a box around that. X plus 5 over 2, and then plus 1. In order for you to add fractions together, what has to happen? Like, why can you add fractions together? Maddie? Yeah, you have to have common denominators. So if you have 1/2 and you're adding 1 to that, I always make that other value a fraction as well. Because if you have a fraction and you're working with another value, you might as well look at that other value as a fraction. So I'm going to make this 1/1. So that now I have these two fractions that are sitting next to each other. Maddie, if the denominator right here is a 2, and we have to have a common denominator, this 1/1, what do we have to do with it to get a common denominator? Multiply it by 2. So if I'm multiplying 1 by 2, it becomes 2/2. It's still the number 1. It's equivalent because 2/2 is 1. We just are writing it a little differently so that we can have a common denominator with our fractions. So that's the only way that you can combine fractions together. Now when the denominator is the same, what do you do to combine them together? Melanie?
You just have the numerator
Right. So a common denominator works with fractions. The bottom stays the same because that's the common part, and you add the numerator together. So like this 3 is just kind of hanging out on the top. But now we have x plus 5 plus 2, adding the pieces that are like terms, that makes that x plus 7, and then it's still over 2. Questions? All right, so I've been saying that fractions are really picky. When we did radicals in chapter 5 and at the beginning of this chapter, you can't have a square root in the denominator. You're not allowed to have a negative number in the denominator. You're also not allowed to have a fraction in the denominator. A fraction in a fraction isn't allowed. And that's what's happening here. All of this is the denominator, but it's a fraction, and we're not allowed to have that. So we're going to try and get rid of that fraction, or get rid of the denominator of the denominator, and that's this 2 here. So if I want to get rid of a 2, and it's a fraction, this is really saying you're taking x plus 7 divided by 2. What's the opposite of division? I heard somebody quietly say it. Maggie, what's the opposite of division? Multiplication. So whatever you do to the bottom of a fraction, you have to do to the top of a fraction. We did that same thing with radicals. If we wanted to get rid of a radical, we multiplied the square root. Well, I want to get rid of that bottom of the fraction. Whatever's in the bottom of the fraction, I have to multiply by it to get rid of it. But we have to make sure we do the same thing to the top as well. So the top becomes 6. This cancels because you're multiplying by it to get rid of it. That's the whole goal. I was dividing by 2, now I'm multiplying by 2, and they eliminate. So we have a 6 on the top, and then x plus 7 is left on the bottom. And we no longer have that fraction in the denominator. Questions on number 14? Did any of you figure that one out? So those are like good. Emma, maybe? Yes. I thought I saw her little hand peeking up there. Those are really good algebraic problems. I know we haven't worked a lot with fractions, but just trying to like think about what do you have to do to have a fraction, trying to work through them. So let's work through 18 because I think 18 is similar. It involves fractions as well. So if you look at 18. Number 18 says g of x. And again, just a reminder that g of x is 3 over x plus 1. So working through the problem the same way, we have this composition or composite function. We're going to take out the inside and replace it with the g function. So instead of g of x, the equation is 3 over x plus 1. Now what do you do with it? Because there's still a g outside, and inside we have this 3 over x plus 1. So what do we do next? Or what would it look like? How would you plug it in? Connor, you want to take a shot at it?
Name the value
Where does the 3 over, where does this go?
where x is.
Where x is. So wherever x is what it's going to replace in the parentheses. So this says 3, and then here's x plus 1. So wherever x is, this replaces. So x becomes 3 over x plus 1. So this is supposed to be 3x plus 1. This is x. It's still x, but we replaced it with that quantity that was in parentheses. So now we're using the same fact that we used above in number 14. It looks similar. We had x plus 5 over 2 plus 1. So we now have 3 over x plus 1 plus 1. So we're going to use the same common denominator fact. I'm going to make this into 1 over 1. Whatever's in the left denominator has to be on the right denominator. So if there's an x plus 1 in this denominator, my second fraction has to also have an x plus 1 in it. If this was a 7, I'd have to have a 7. If it was a 3x, I'd have to have a 3x. The denominators must be the same in order for you to add them together. So that means that this needs to become x plus 1, and this also has to become x plus 1. So whatever's in the one denominator, you have to replicate in the other denominator. That's what a common denominator means. They must be identical. And because it's just a 1 there, you're just taking 1 times x plus 1. Well, it stays the same. It's that x plus 1. So Melanie, I think you answered the last question. When the denominators are the same, what can you do? Add the numerators. So if we add the numerators here together, Melanie, what do you end up getting? Yeah, you end up getting 4 plus x, and then it's x plus 1. So the denominator's the same. It doesn't change. That's the common denominator part. When you're adding fractions, the denominator, once it's common, it just kind of moves over. You're adding the tops together. All right, the next fact that we're going to use that we did above, so very similar problem, we now have this fraction in the denominator, and that isn't simplified. We're not allowed to have that. So in the one above, there was a 2 in the very bottom of the fraction, and we multiplied the top and the bottom by 2. So whatever's in the very bottom of the fraction is what we have to get rid of. Well, there happens to be an x plus 1. That's okay. Whatever's down there, we need to multiply by. So multiply by x plus 1, multiply by x plus 1. So whatever is in the very bottom of the fraction, we need to get rid of. It can't stay there. So these cancel, because multiplying is the opposite of dividing, and that gets rid of it. And anybody tell me what goes on the top if I have 3 times x plus 1? What does that become? Julian? And then on the bottom, Julian, is now just x plus 4. So that one's definitely a challenge problem. Probably in that, like, if Mrs. Kane gave bonus problems. Questions? Is there any others that you wanted to go over? No. 22? So 22 says we're taking g of x divided by f of x. Melanie, can you tell me what you plugged in for g of x?
2x.
And what did you plug in for x of x? F of x. So we have g of x divided by f of x. In order to actually divide, whatever you do to one thing, you have to do to all of them. So are they all divisible by 2? Do they all contain an x? No. So is there anything you can do to this problem besides write one thing on top of the other? No. This is your answer. That's as far as you can go. There's nothing else you can do with that problem. So it literally is placing the one function on top of the other and then knowing that you can't do anything with it because they all don't have something in common. Questions on that? So that one seems like you should do something else with it because all the other problems we've done something with. But that's actually as far as you can go. So I'd like you to make sure that your name is on that homework, and I'm going to kind of take a peek at it. Oh, thank you. So in your packet, we're going to start inverse functions today. So we're working with trying to do different operations with functions. So we've added, subtracted, multiplied, divide. Bless you. Now we have this composite function where we're trying to use substitution. And now we're going to talk about what an inverse function means. So if you have the inverse of something, like what's the inverse of addition? Holly? Subtraction. What's the inverse of multiplication? Division. And let's talk about, I'll write it over here. Maybe. Oh, now it's up there typing. It's just a little slow. What's the inverse of x squared? Julie? The square root of x. Because that's how we get rid of it. So an inverse is like undoing your operation. It's kind of like thought about the opposite operation. So an inverse relation, you can kind of think of it as like the opposite relation, or we're going to say that it interchanges x and y. Or the input and the output values. And I'm going to show you a little example over here. So if we have a set of ordered pairs, say -8, 3, there we go. So this is a set of ordered pairs. This is called a relation. A relation is anything that takes an x and pairs it with a y, or takes an input and pairs it with an output. That's a relation. So here we have a relation. I just picked 3 ordered pairs. To find an inverse relation, we're going to interchange the x and y, or we're going to switch the input and output values. And it's really that simple. So if this is my function, or my relation, and I want to get the inverse, literally, you interchange x and y. What does that mean if I say interchange x and y? Julian? You switch them. So the inverse would be 2, 3, -7, 6, 3 comma negative 8. Literally, you're switching, flipping, changing x and y. That's how you find an inverse. So multiplication and division are inverses. Addition and subtraction are inverses. X and y are inverses. So an inverse relation or an inverse function looks like f with a little negative 1. And then we have that x inside. So a regular function is of the form f of x. So this is our function. We say it's a function because it passes the vertical line test. Each x has one y. Once we interchange x and y and find the inverse function, we have a special notation for that. And this little negative 1 represents the inverse function. So the variable outside, or the letter outside, that f, says that the functions are related. The little negative 1 is the actual inverse part. That's the inverse notation. So once we find an inverse, now we can kind of give it a special name. So the negative 1 makes it the inverse. The f says they're related to each other. One function was created or derived from the other function. So there are some steps down below to help us find the inverse function, which is going to kind of be like the opposite function. So when we look at them, they should kind of look like opposites of each other. So it says, if you start with f of x, so if the equation starts out with f of x, we're going to switch it back to y. F of x and y are the same thing. F of x says we have a function, y is just a y. It might be a function, it might not be. The second step, we're going to switch x and y because that's how you find an inverse. You flip-flop x and y. We're going to solve the equation for y to get it back in y equals. And then once we have that solved, y by itself, we're going to go back and use inverse notation. So it seems like it's 4 long steps, but like 2, the first and the last, are pretty straightforward. And switching x and y are also pretty straightforward. So if you look at the 2 equations that are underneath, it wants us to find an equation for the inverse of the function. And the first one starts out already in y equals form. So we don't have to change anything, it's already y by itself. So the second step says switch x and y. Literally, you're going to switch them. So if this says y, we're making it x. That's how you find an inverse. You're pretty much doing the opposite. So the opposite of y is the x variable. You're keeping the 3, but we're changing x to become y, and then we have a negative 5. So inverse is another way of saying kind of like the opposite. Our goal is to try and find an opposite equation. Now you need to solve for y, get y by itself, because we're going to come up with this new equation that's related to our original, but they should be inverses. So Abby, what would you do first to get y by itself? Yeah, let's take that 5 to the other side. And Abby, what else would you do to get y by itself? Divide by 3. So now we have x plus 5 divided by 3 equals y. So we got y by itself. The last thing to do is to make this inverse notation, which means take this y out and write it as f negative 1 of x. So just kind of comparing what we started with to this new equation. So we started multiplying with 3. We had 3 times x. Now we're dividing by 3. We said multiplication and division were inverses. We had a minus 5. Well, the opposite of subtraction is addition. So now I have the total opposite function or opposite equation. So therefore, it's an inverse of what we started with. So this is an inverse function. See if you can find the inverse for letter B. So the first step would be to make that a y. And I don't rewrite it, I just usually throw a y right on top of it. Switch the x and the y, and then get y by itself. So Odette, what would you do first?
I subtracted the 2.
And then
Multiply by 4.
multiply by 4. Because right now it's 1/4. So multiply by 4. And Odette, what does the left side become if you multiply by 4?
4x minus 8.
Nice job. Remember, everything's getting multiplied by 4. Not just the x, but also the -2. So you have to make sure you're keeping it equivalent. Every piece gets multiplied by 4. And then writing it as an inverse, we have 4x minus 8. Now this one's a little trickier because we were adding 2, but now we're subtracting 8. That's because we have to multiply the whole thing by 4. So we had that +2, yes, a -8, because 4 times 2 does give us the value of 8. Questions? So that's the process of finding an inverse. As long as you remember you got to switch x and y, get y by itself, you have found the inverse. So these two functions are inverses of each other. So the next thing that we're going to talk about is how we can kind of go about showing that they are in fact inverses of each other if we don't initially find it. So it says inverse functions. Functions f and g are inverses of each other provided. So I have two equations. They're inverses of each other if f of g of x, that's that composition function we just did, that we did yesterday as well, is equal to x. So when we take one function and substitute it in the other, they're going to break down just to the variable x. And g of f of x is also equal to x. Meaning if you flip-flop them and find the composition of the function, they should also be equal to x. It says the function g is denoted by the f -1 and read as f inverse or the inverse of f. So once you know that they're inverses, we use that inverse notation. We have f of x versus the f -1 of x. So the example down below is a little different than the one we just did above because we're given two functions and it wants us to verify. Verify is the friendly way of saying the P word from geometry. Did anybody have Mr. Warnock last year? No. He loved doing proofs. It's like his favorite thing is to prove. And you should have done proofs last year in geometry. Depending who you had, you might have done more than others. But verify is our algebraic way of saying prove. Prove means you need to show that two things are true. And in this case, we're going to show that they are inverse functions. The way we're going to show that is by using that fact above. So we're going to see if we can prove they are inverses by taking f of g of x and checking to see if that equals x. And by using g of f of x and checking to see if that equals x. So the first thing I'm going to do is I'm going to change this inverse function and I'm just going to replace it with a g so that we can try and do this f of g of x part. And that's what it says. The function g can also be written as f -1 of x. So from yesterday, we're going to try and do f of g of x. That's the first step. So prove means show, verify. See that it works, check that it works. So we're going to take out the g function and replace it with its equation, 1/3 x plus 5/3. I know there's fractions, don't get too worried. All right, what do we do with that 1/3 x plus 5/3? So there's an f outside. So what do we do with that? Mackenzie Myers, what would we do next? Yeah, so right here, for the x, we're replacing it with everything that's in parentheses. So we have a 3, and then we have 1/3 x plus 5/3. Because it's supposed to be x. All of that is x. And then it says -5. All right, so now here's your little bit of mental fraction work. If a 3's outside, that means we need to distribute it inside. So Mackenzie Myers, what would be 3 times a third x? Yeah. So she said it would be 3/3, which is really 1, and then we have an x. All right, Mackenzie, what's 3 times 5/3? Good. Not 15/3. So she said that becomes 15/3, which is just 5. And then outside is a -5. So Mackenzie, that simplifies to become just x. All right. We did half the proof. We verified half of it. But you have to do both because both of them need to equal x. So now we've showed that right now f of g of x equals x, which would be partway, halfway to proving that they're inverses. And we're going to flip-flop it to make sure the other way is also an inverse. So now we're putting the g function outside and the f function inside. So taking out f, replacing it with 3x minus 5. And just like we did above, now we're looking at g. And wherever there's an x in the g function, we're replacing it with this 3x minus 5. So it has 1/3, and then x is 3x minus 5, and then plus 5/3. So, Matt, 1/3 times 3x is 1/3 times -5. And then that simplifies to become x. Because these guys cancel, and you just get x. So, verify. We've now verified. Again, a friendly way of saying prove. We've shown that both of these functions are inverses because they're now both simplifying down to the value of x. And that's the definition, the true definition of an inverse. Two functions are inverses of each other if f of g of x equals x and g of f of x equals x. That's the definition of two functions being inverses of each other. So there's one other problem at the top that I wanted to look at today, just to kind of make sure everybody's good with these problems. There are 3 up here. We're not going to do all 3. Let's do the one in the middle. So the directions are multi-step. This is actually a big problem, and I don't think I left you a lot of work or a lot of space to work. So we'll kind of just, we definitely won't be doing A. So we'll cross that out. Maybe we'll do C tomorrow. We'll see. So the directions say find the inverse of the given function. So we don't know what the inverse is, we're going to find it. Then verify your result and the original are inverses. So how do we answer the first step of that? Find the inverse of the function. What do we do to get that, Captain? Perfect. So set f of x equal to y. And then what else, Gavin? Switch x and y. So the first step, we need to find the inverse. We don't know what it is. After you've found the inverse, use that inverse notation. So we have x plus 1 over 2. So it looks like the inverse, it's pretty much opposite. We were multiplying by 2, now we're dividing by 2. We had a plus 1, or a minus 1, now we have a plus 1. So this is the inverse of the given function. So we did the first part there. The second step says verify your result and the original functions are inverses. How are we going to answer that part of the question? So how do I verify that they're inverses? Julian?
You can start by using, plugging in x plus 1 divided by 2 into the x and then those equations.
Right. So we're going to take that f of g of x. So he said take x plus 1 divided by 2 and plug it into the first equation. So that's the f of g of x part. So Julian, if we have a 2 on the outside and x plus 1 divided by 2 inside, what can we do to make that a little simpler?
The twos and these cancel out.
Yeah. So don't over complicate the problem. If you're multiplying by 2, which is really 2 over 1, and dividing by 2 on the inside, those 2's cancel. Multiplication and division are inverses. So then we're just left with x plus 1 minus 1, which is x, because those 1's cancel. So if there's a multiplication on the outside and division on the inside and you're using the same number, they cancel out. And then the last step would be to take g of f of x. So we're going to do the exact opposite that we just did. So we have 2x minus 1 plus 1 and then divided by 2. All of this is the x right here. We're plugging it into that x. So minus 1 plus 1 cancels. That gives us 2x divided by 2, which is just x. Verify means that they both should equal x. So there's a multi-step problem there. We found the inverse. And then after we found the inverse, we had to show that they were inverses of each other. So I originally had bookwork for today, but I have a bunch of worksheets copied, and I thought I'd rather do a worksheet than bookwork. So you're doing the back of the worksheet that's labeled 6.3, and you're doing the front of the worksheet that's labeled 6.4. And it deals with inverses and those composite functions, the f and g of x. So the side that I kind of passed out, like you're doing the 4 questions on the back. There are 4 questions with composites. And then the one that's labeled 6.4, which is the one you're getting right now, you're doing the front of this. How many did I give you? So we're good? I have an answer key as well. On your way out, you can grab it. I'll put it right here by the table. Grab the answers on your way out. Please check those answers. Have an awesome day.